Differentiability, and differentiability means that you can find the derivative of a function. Now, a function can be differentiable at several points and not be differentiable at one point in the function. Okay, but it can be differentiable for all values. Usually, if something is differentiable, it is smooth at that point. So, like polynomial functions, like something that looks like that is always differentiable. Okay? Logarithmic functions that look kind of like this, those are differentiable for all values except to the left of 0 or at 0 and right up to 0. So logarithmic functions are pretty much differentiable. Exponential functions pretty much are differentiable for all values. Okay? That's like exponential. Polynomial functions that look like this. Rational functions are differentiable, but a lot of times they'll have asymptotes, so they won't be differentiable at certain points in the function. Okay? But here you can find a derivative, and here you can find a derivative. Okay? Okay? So just at certain points. Things that are not differentiable. And this section is more about differentiable, about things that are not, finding things that are not differentiable than where they are differentiable. Because you can't always find the rate of change of something, which is what you're trying to find when you're finding if it's differentiable. For instance, this thing that looks like this, we'll do it in purple. That's not purple. Is that function differentiable? It's not smooth, and also the slope going into this, it's not differentiable right here because the slope coming into this point is what? Negative. It's negative, and the slope going out of this point changes abruptly to positive, right? So right at 0, this would be like y equals absolute value of x or something like that, right? So the slope here might be -1, and the slope over here would be +1. And it's differentiable about over here. The rate of change is always 1. The rate of change here is always -1. But right at that point, since it changes abruptly, then it would not be differentiable. I could still sketch a derivative. The derivative would probably look something like this and like this. Do you understand that? Okay. Because the slope is, no, you would not have a point at 0 because the derivative is undefined at 0. Okay. So you're not talking about, you're talking about the derivative. Okay. So there is no derivative exactly at 0. It's undefined. Okay. So not differentiable, another type of function that's not differentiable would be something that looks up. It's going to put arrows on that end. We want arrows on both ends. Okay? Something that looks kind of like this. Have you ever seen a function that looks like that? That thing is called, this point there has a name. This is called a cusp. In the book, they call this a corner. Okay, this is a corner when it's just straight in, straight out. When you have a slope coming in like this and going out, and an example of something that has a cusp might be like y raised to a fractional exponent, like y equals y or x raised to a fractional exponent. That would actually start here. Okay, this would be shifted over, but something that has a fractional exponent has cusps in it. Okay. And it's not differentiable because the slope coming in is very negative here and very positive going out. Okay? Other things that are not differentiable are what else? Things that have infinite slopes. There are certain functions that have infinite slopes, like this one. There's a function that goes like this. And then right as it comes into 0, it gets like infinitely steep straight up. And then it kind of goes like that. Anyone? Whoops, that's kind of messed up there. But does anyone know what that function is? Just to tell you.
Tangent?
That's, yeah, maybe, very good. Like, well, not tangent, but I think inverse tangent?
It's either that or one. Yeah.
Inverse tangent would look like that. But also things like y equals the cube root of x would look like that. And also, yes, y equals inverse tangent. Do you remember that? Inverse tangent of x would be another example of something that has an infinite slope at a point. All right? So, not differentiable, infinite slope. Infinite slope. Right? Slope. I don't know how to slope. Okay? Right there. Okay? But, and also, if something is not continuous, then it's not differentiable at that point. So for instance, if you did have a function that looked something like this, where it comes in here, and it has a jump like that, which we've seen lots of ones like that, and this is point C, it might be differentiable everywhere else, but not diff at x equals C. Okay? So not different, you can't find the derivative there because even though the slopes might or might not be the same, it's not differentiable. Okay? And so in order for something to be differentiable, okay, the limits as x goes to a, of f of x minus f of a over x minus a must exist, okay? And what that means is that the limit from the left, so remember, in order for a limit to exist, it needs to be the same from the left as from the right. So if the slope is not the same from the left and from the right, then the limit does not exist. So you might have a question like this. Find where f of x equals the absolute value of x minus 3 minus 2 is not differentiable. Could you do that? Without, you don't have to plug into this formula or anything like that. You guys, you could do it graphically, right? So you want to think about things in the quickest way possible. You don't want to do like the limit process unless you have to. So what does this look like? What does this look like? Please tell me what this is. It's a v, and where is that v?
3, negative 2.
At 3, negative 2, right? So, whoops, that's not a very good v. But, so where is it not differentiable? At x equals what? At x equals 3. That's all you have to do is kind of sketch a graph. Since the slope coming in from the left and the slope coming in from the right are different from both ends, then it is not differentiable. Okay? So at x equals 3 is not differentiable. You might have something that looks like this. Find where, or find if, or tell why, or show that. Show that, not find it. Show that f of x equals x cubed if x is less than or equal to 0, and 4x if x is greater than 0 is not differentiable at 0. Okay? Could you do that?
Yeah, you can graph.
Well, you could graph them, yeah, but you could also actually find the derivative at those points. Well, do these two functions hook up at 0? Hook up. They're going to hook up. All right. At the prom. At homecoming. Okay. Y equals x cubed. What does that look like? Y equals x cubed. It does this, right? Does that. Okay? Does that. But it only does that until I get to 0. Why? Whoops. I hate when that happens. Okay. I can fix it. There. I can fix it. I just need a smaller eraser. But it doesn't do that. Okay. Oh well. After x cubed, it turns into y equals 4x, which looks like what? A straight line, which is 4x, which looks like that, right? So it appears that these don't have the same slope, even though they do. If I plug in 0 in here, what do I get out? If I plug in 0 in here, what do I get out? So they do meet, okay? But differentiability is different. It's do they meet and have the same slope at that point, okay?
So if you did the derivative,
so it would be different at 0, right?
Yes.
At 0, it would be different value.
Yes, if I did the derivative at 3 from a previous problem, we found the equation of the derivative of this, which is 3x squared, okay? If I plug in 0 in there, so f prime of 0, if I did do the limit process, comes out to be what? 0. And f prime of 0, it's actually, as I come, this is coming from the right, and this is coming, this one is coming from the left, and this one is coming from the right. What's that equal to? 4, right? Because this is a line where the slope is always 4, right? So because this and this are not the same, then it's not differentiable. Also, you can see it graphically. This thing
So if you asked us that, would it be show algebraic?
might be both.
Okay.
Okay? Bicycle fork, Davis, has to be differentiable to be a good bicycle. Back in the olden days, when they used to make bicycle forks out of metal and stuff, they used to look kind of like that, They had little curvy things on the end, and this is a straight line, right? And this is a curvy piece. And they would weld these two things together in order to have a nice fork. This slope has exactly match up with that slope, And so that's kind of a real life case of differentiability. Yes, sorry, Caroline.
So if I look at the graph, you can tell just because this.
Yeah, if you looked at the graph, it said tell whether they're differentiable. You could say no, they have different slopes going in and out. Okay, but if I said show algebraically, that's how you'd have to do it. I mean, there's always more ways than one to solve these problems. Okay, then they have the idea of local linearity. Local linearity, okay? And this is why, who was it? Back when Columbus went to discover America, what did he try to prove?
Earth was round.
That the Earth was round, right? But why did everyone think that the Earth was flat? Yeah, because they didn't go up in airplanes and they didn't go up in spaceships and they couldn't see that the Earth was round, right? But some mathematicians or physicists or whoever they were, they figured out that they kind of did some math and they figured out the Earth had to be round. But the idea of local linearity is kind of the same idea. If you have a curve, okay, and maybe it looks like this or something like that, and I want to find the tangent line at a point on that curve, okay? If I want to find the tangent line at a point, so let's say this is the tangent line at this point. If I were to zoom in, okay, on this little area right here, okay, watch this high-tech gadgetry, if not very good. Sorry, let me go back. Let me try to go back again. If I were to zoom in on this little area right in here, okay, it might appear that very close to this curve, what seems to be the case about this line and this curve? That they're the same. And that's the idea is when you get very close to a curve, the tangent line actually approximates that curve. And they use that to find numerical derivatives and something called the symmetric difference quotient. All right? So local linearity is just the idea that as I get very, very close, zoom in on that curve, that the tangent line and the curve look kind of the same. Okay? And then they use that to calculate something called the numerical derivative. Okay? But first they start with this thing called the symmetric difference quotient. Symmetric difference. Uh-oh.
Oh, yeah, I have no idea.
You have no idea about what?
No, I was just talking to Shappy real quick.
Okay.
Yeah.
Remember, you're on tape right now. Okay. F of A plus H minus F of A minus H over 2H. So this comes from if I have a curve, okay, and I want to find the slope of that curve at some point. Let's go the other direction. I'm sick of going uphill. Let's go downhill for a while. So say I want to find the slope of this curve at some point A. What we've been doing is going ahead H, right? And then finding the limit as H gets very, very, very close to A. What you can do to be a little more accurate, okay, is to go symmetrically a little bit. Oh, that's not, let's undo that, okay? If I go a little bit behind that point A and a little bit in front of that point A, I can get kind of a better picture of what the slope actually is at that point. Do you understand that? And as I get closer and closer and closer and closer, I get closer and closer and closer to the actual slope at that point. Okay? So that's a symmetric difference quotient where the distance from here to here is h, and the distance from here to here is also h. So this point right here would be a minus h, and this point over here would be a plus h for the x coordinates, right? And then the y coordinates would be f of a plus h minus h. So the distance between those 2 points is 2h. You understand that? Okay? So your calculator actually puts a number in there and then use 0.001. So the numerical derivative and numerical derivative on your calculator is defined as, okay, f of a plus 0.001. Your calculator just uses 0.001. And I don't know if there's a way to change that, but f of a minus 0.001 over what? If h is 0.001, what's 2h?
0.002.
0.002. So your calculator can find approximate derivatives and get very, very, very close. Sometimes you can't even tell the difference between the actual derivative and your calculator derivative using this idea of a difference quotient. But what you have to realize is that your calculator is still approximating. It's not finding, it won't find the equation for you. It will find the derivative at a point. Okay? So for instance, here comes your calculator. Okay? Don't fall asleep. Here we go. And depending on which mode you're in, okay? First I'm going to find the, let's not go to this one. Let's do y equals x squared. Good. X squared. Okay? So I'm going to plug the function and say I want to find find ender of f of x equals x squared at 2. Okay? Watch what you can do. So what your calculator is doing is going 2.001 squared minus 1.999 squared over 0.002. So the way you do that, okay, first you plug in y equals x squared, then you go to second quit, then you go to math. And I'm in classic mode. There's also the other mode where you plug into the boxes. If you want to change the mode, that's okay. But I like the classic mode because I'm kind of old school, you know. So, and this is the way I learned how to do it. Numerical derivative. So you go to n deriv, and you hit that, and then you go to you got to plug in the function. You can either directly plug in x squared, or you can plug in y1. So I'm going to do it that way. Bars. Y bars, you've done this before, right? Function y1, and then I have to go comma, and then I have to go x. So that means the derivative with respect to x at 1, or at 2, I was going to find it, right? So some of you know the power rule. What's the derivative of this? What's it? 2x. And so 2 times 2 should give you 4. And so if I hit enter, I hope that I get 4, which I do. Okay? And yes, ma'am.
Will you show how to do it if you're not in classic mode?
Yeah, you just go to mode. It's really the same idea. You go to mode. You have to go down here. Where is it? See where it says math print mode? Whoops. Up here. It's kind of more work, I think. And so then you go second quit, and math 8, and you just plug in bars, y bars, function y1, or you can plug in your x squared in there, and then you just plug in x in here, and then so again I'll just do it. Okay. Oh, it should be dx. The derivative with respect to x. Okay, what happened? Math 8, right? You want the derivative with respect to x, okay, of x squared. So I have to go to here. So I'm going to go bars, y bars, function, y1. And then I'm going to go at and then I go at 2. Okay? And then I hit enter. Whoa! What did I do here? What did I put down there? I put an X.
There's always a D.
Is that a D? Should I change my...
Just X squared.
It should have worked. It should have 4. Anyway. That's how you do it. Why didn't it work? dx not time to go yet. Okay? So it should work. ddx of x squared, put in at 2, and you should get out 4. Should. Did it work?
Yeah.
Okay. So you guys see, it's hard to push the buttons on this calculator. Not time to go yet. Not time to go yet, okay? So, just to show you, if I change this function, let's just do it with a different function. Oh, because I put my derivative into y1. I need my function in y1, not my derivative, okay? So, just for fun, put in a different function, like y equals natural log of x, okay? ln of x. And if you remember ln of x, I don't want ln of x squared. I could do ln of x squared, but I don't want to do that. Okay? And if you remember, delete. If you remember, ln of x looks like this. So the slope goes up kind of fast at first and then slows down. Okay. Zoom 6. So it looks like that. So say I want to find the derivative at 3 or something like that. So I'm going to go second quit. Here I'll plug it in there. dx y1 at x equals 2. It'll change, and I get a decimal number. Okay, so the derivative of natural log of x at 2 is 5. Now be careful. I'm not going to show you. It's not, because this doesn't always work. Because say I put in y equals, I just want to show you the last thing, okay? Hold on, I got 3 more minutes. Say I did math number absolute value of x. Want to delete this, okay? Delete that. I just want plain old absolute value of x, okay? And, okay, second quit. And say I want the numerical derivative of that function. I could go here, and I could just second entry. And I want to find the numerical derivative of this function at, not at 2, but out at 0, okay? So what should be the numerical derivative of absolute value of x at 0? 0. No, it should not be 0. But it says it's 0. Should I just go with that answer?
Yes.
No, because the calculator is wrong. Listen up, okay? Because absolute value of x looks like this. When you zoom in infinitely, it's still going to look like that, right? So even if I go 0.01 here and 0.01 here, it's still going to give me a slope of what? 0, because I'm subtracting this point minus this point and dividing by 0.02. Undefined, right? Because the slope is different right now. Your homework is on the website. You can work. All right. Oh, end the recording. Stop.